Hello everyone, in this video we are just going to use the timer peripheral in STM32F4 series microcontroller for writing our own accurate time delay generation function in our Keel Microvision IDE. Let's get started. So in this video what we're going to do is we are just going to write down the base drivers from scratch for the timer peripheral of the STM32F4 series microcontroller, and using the base drivers that we are going to develop, we are just going to write down our own accurate time delay function, that is millisecond time delay function, which is mostly accurate. So we are just not going to use any of the third-party libraries, or we are not going to use any of the HAL libraries or HAL APIs, and everything we will be writing down from scratch. So I'm just going to open the Keel Microvision IDE and let us just configure the project for the microcontroller STM32F446RE. Now I am just opening the Keel Microvision IDE. So here, once the IDE is open, just click on the project tab and click on new microvision project for creating your new project, and move to the respective folder where you want to store your project in your local, and provide a name for your project right over here in the file name tab, and then click on save. And in the next consequent tab that is popping out, you just want to select the microcontroller that you are working on. So in our case, the microcontroller is STM32F446RE. Just type in the microcontroller name. I'm just typing in like STM32F446 in the search box, and here you can see you are getting the microcontroller that you typed in the search box. Just click on the plus icon near the microcontroller, and here our microcontroller series is STM32F446RE. Just click the plus near the STM32F446RE and select the microcontroller right over here inside that tab, and then click on OK. And in the next manage runtime environment tab right over here, you just want to select the CMSys driver and the startup code required for the microcontroller. So just click on plus icon near the CMSys right over here and check this code right over here. And after selecting this, click on the plus near the device and then click on the checkbox near startup for generating the startup files required for the STM32F446RE microcontroller, and then click on OK. You can see the project has been created right over here in the project pane. Just click on the plus near the target for revealing all the project files, and then right click on the source group and click on add new items to group source group 1, and here I just want to create my main.c file required for the project. So click on the .c format right over here and provide a name for your file that you are creating in the name search box right over here. So I'm just typing the name of the file that needs to be created to be main.c. Just type in main, since we have already selected the extension to be .c, and then click on add button right over here for adding the main.c file to your project. Click on the plus near the source group 1. You can clearly see the main.c file has been created to your project. And as a first step, we are just going to create or write down our main function. So I am writing like int main of void. So this is the main function which will be containing the logical part of the program which needs to be executed in our microcontroller. And inside the main, I am just going to create the while of 1, which is the infinite loop of the program. So this while of 1 is nothing but a never ending loop or infinite loop or super loop, whatever you call it. This is an infinite loop which will be containing the logical part of the program which needs to be executed again and again until the microcontroller is stopped. And the portion of the program just before the while of 1 inside the main function will contain the configuration lines of the program which needs to be executed only once in the lifetime of the program initially. So there are two segments of an embedded program. One is the configuration segment and another one is the infinite segment. So in configuration segment, before the while of 1, we will be writing down the configuration lines, such as, for example, configuring a port, configuring timers, configuring communication protocols, etc. Just before the while of 1. And another segment is nothing but the logical segment, which needs to be executed again and again until the microcontroller is stopped. So that part of the segment or that part of the program we will be writing down inside the while of 1, which is the infinite loop of the program. That's all about the main function creation. And now I'm just going to add the header file required for the project. So has include of STM32F4XX.h. So we can either use this particular common header file STM32F4XX.h, or you can use another header file available which is particularly meant for this STM32F446XX.h, which is particularly meant for this particular STM32F446RE microcontroller or any other STM32F446 series microcontroller. So I am just going to use this particular header file which is available specifically for this microcontroller, and that's it about the initial configuration needs to be done in Keel Microvision IDE. So once you are done with the main.c source file creation and all the main function creation right over here, I just want to do some basic configurations required for interfacing the board to our microcontroller, that is the Nucleo board or any other custom made STM32 microcontroller based board to your PC. Just click on the options for target icon right over here and click on output tab in this particular window zone right over here and check this create hex file checkbox. That's it. Now click on OK. Save the configuration, and now let us start writing our logical part of the program as per our requirement. So I deleted everything right over here in the main.c file, and for reference I am just going to take the LED blink program that we wrote in the previous one of our lecture of interfacing LED with STM32F446RE microcontroller in the same series that you are watching. So go to the same playlist of the videos, and in the top you can find the interfacing of LED with STM32F446RE microcontroller. So in that video we just derived and wrote a program for blinking the onboard LED in the Nucleo F446RE microcontroller development board. So we are just going to utilize the same program and we are going to alter the program for blinking the same LED for accurate time delays. So let me just open that program. So this is the program that we wrote. I'm just going to copy this and I'm going to paste it right over here. So this is the program that we wrote in the lecture of interfacing LED with STM32F446RE microcontroller. So in this program you can clearly see this is the configuration part of clock of the microcontroller. This is the configuration part of enabling the GPIO-A clock, and these three are the configuration for configuring the PA5 pin of the microcontroller as output pin. Since PA5 is a pin to which the onboard LED that is available in the Nucleo development board is connected, we are just configuring that particular PA5 pin as output pin, and then we are toggling the state of the pin for rough loop delays for blinking the LED. So inside the while of 1, that is the logical part, you can clearly see we are turning on the PA5 pin, waiting here for a rough delay, turning off the same pin, waiting here for the same rough delay, and as soon as everything is completed, execution in this while of 1. Since this is an infinite loop, the control comes over here to the first line of the loop and the process continues. So the blinking operation will be held in the development board LED, which is connected to the PA5 pin of the microcontroller. So this is what the program means. So now what we are going to do is we are just going to alter this particular delay function for producing accurate time delays, accurate millisecond time delays using the timer peripheral of the microcontroller. That is what we are going to do. Instead of this rough delays right over here, we are just going to toggle the state of the LED using accurate time delays. So I'm just deleting this one delay, another one delay. So before going to the configuration of timers, let us test whether this program is working. Just compiling this program. You can see the program is compiled with 0 errors and 0 warnings. Now I am dumping the flash to the microcontroller development board Nucleo F446RE. I have already connected the Nucleo board to the PC through USB cable. Now when I reset the board, you can see the onboard LED is blinking at a rough loop delays. So the program is working as expected. So now we are just going to configure the timer and then we are going to replace this particular delay right over here in between these two programming lines with accurate time delays. So for configuring the timer, I have derived few steps. These are those steps. Let me just copy all these steps and I am going to paste it below the configuration segment of the program just above the while of 1. So these are the steps that we need to follow for configuring any timer in the microcontroller. The first and foremost step that we want to do is we just want to turn on the clock for the timer. So let me just open the user manual of the microcontroller, and in the user manual you can find the particular register called APB1ENR in the RCC peripheral. So in this particular 32-bit wide register APB1ENR, we can clearly see the bit number 0 of the register is timer 2 enable and bit number 1 is timer 3 enable, bit number 2 is timer 4 enable, and so on. So since I'm just going to configure timer 2 right over here, I'm just going to turn on the bit number 0 in this APB1 ENR register for enabling the clock of timer 2. If you want to configure or enable the clock of any of different timers right over here, you just want to enable the respective bit numbers in this register. So since we already have experience in configuring the RCC peripheral registers, the pointer used is RCC inside the CMSS file of the silicon vendor. So RCC, I'm just going to point to APB1 ENR. I'm going to turn on the bit number 0 for enabling the clock of timer 2. Since we decided to configure the timer 2 for generating accurate delays in our program. And the next step is moving to the timer peripheral. Till now we just configured the RCC peripheral and all these steps needs to be done in the timer peripheral of the microcontroller. So next step is we just want to disable the timer counter before enabling or setting the parameter values for the timer. So moving to the user manual, I'm just going to move to the chapter general purpose timer TIM2 to TIM5 and I'm clicking on the timer 2 to timer 5 registers, and the first and foremost register is control register 1 of timer. So TIMX control register 1 means the small x right over here denotes the timer number. So if you want to configure this particular register for timer 2, you just want to use the timer 2 pointer and you can write to the register values. If you want to configure this particular register for timer 3, you can do the same with the help of timer 3 pointer. So each timer will be having a pointer, and if you utilize that particular timer will be configured. That's it. So in this register, you can see the bit number 0, that is CEN. Let us discuss about the description of this bit number 0. So this particular CEN is nothing but counter enabled register. So when I write 1 to this bit number 0 of this register, that means the counter of the timer is enabled. If I clear this particular bit number 0, the counter of the timer is disabled. That's it. So as per our steps that we want to perform, we just want to clear the control register 1 bit number 0 for disabling the timer counter for timer 2. So the pointer that we want to use for timer 2 is tim2. If you want to configure timer 3, you can give like tim3, etc. So since I am configuring the timer 2, I am just using the pointer tim2. So now I am pointing to CR1 and I am going to clear the bit number 0. And you can see the final step right over here is turn on the timer counter, which means the same bit right over here needs to be turned on or return the value 1. So here I am just going to write R of 1 left shifted by 0. That's it. So as the next step, we are just going to calculate and load the prescaler value for the timer. So as we discussed in the previous video, prescaler is just a number or a division factor which divides further the timer clock for reducing the frequency of timer and for increasing the time period of timer. So this particular prescaler decides the time period of timer, or it decides the one tick of timer. So for every timer count value, what should be the time elapsed, or for every count value, how much time must the timer take? So that is decided based on the prescaler value right over here. So now our system clock is 16 megahertz and timer clock is also 16 megahertz. There is no division factor between the system clock and timer clock. So if I assume the prescaler value to be 16 right over here, the timer clock, that is 16 megahertz divided by 16, will provide me 1 megahertz as the timer clock. And the time period of this particular frequency is 1 divided by 1 megahertz, which is nothing but 1 microsecond. So this is the time period of timer, or the 1 tick of timer. So now I am just going to plan the 1 tick of timer as 1 millisecond. So for every accurate 1 millisecond, I need my timer to count one value in its counter. So for that, what I can do is prescaler, I just want to increase the prescaler. So 16 megahertz is nothing but 16,000,000. So 16 megahertz divided by 16 is 1 megahertz. So in this case, I want the time period of timer or 1 tick of timer or my timer to count each step for every 1 millisecond. So what I can do is I can just increase this particular prescaler value to be 16,000. So now if I assume the prescaler to be 16,000, my timer frequency will be further reduced to 1 kilohertz. So the time period of the timer is 1 by 1 kilohertz is 1 millisecond. So this is how you can calculate and load the prescaler value of timer for generating accurate time delays as per the application needs. So I'm just going to load the prescaler value timer 2. I'm just using the same pointer and I'm going to point to PSC, that is a prescaler register, and I'm going to load the value 16,000 minus 1. So this minus 1 is because the 0 value is also a count in the timer. It always starts from 0. So whatever the value that you are calculating, you just load it like the value minus 1 in this prescaler register. And next, coming to the auto reload register. So this register is available like ARR, which is the same pointer, RR. So this auto reload register is useful for loading or generating the update event whenever the counter value matches the pre-programmed value. So here what I will do is I will just add the value to be 1000. So whenever this particular 1000 is matched with the timer count value to be 1000, the compare match happens and the timer interrupt or something will be generated. So that is why we are loading the value to be 1000. So whenever the timer starts, it will start from 0 and it will count till 1000. Again, once the counter value reaches the value in the ARR, that is the auto reload register, the timer counter will be reset to the beginning value 0. And we are starting the timer right over here. The next step that we are going to perform is the writing our own application timer. I'm just bringing that command right over here. I was going to utilize this same function, that is delay function, for generating accurate millisecond delays. So here, as soon as the function enters, as soon as the control enters the function, I'm just going to clear the timer count value. And inside the while written right over here, I'm just going to check the timer count value to be less than the delay value, that is the parameter value. So until the timer count value reaches the delay value, that is the parameter value of this function, this while loop will be true. Once this timer count value reaches the delay value, this particular loop will be exited and the function goes to the next execution line. So since for each count we configure the timer to be producing 1 millisecond, whatever the value that you are passing as a parameter to this function will generate so and so millisecond delay. For example, if I write like delay of 5, we know that, or we configure the timer to for generating 1 millisecond for each count, or one tick of the timer 2 will generate 1 millisecond. So this particular loop right over here will wait until the parameter value that you are passing right over here, until the timer 2 counter value reaches the parameter value that you are passing right over here. So since I am passing the value 5, until 5 millisecond or until the timer 2 counter reaches the value 5, this loop will be holding the execution, and once it reaches 5, this will be releasing the execution of the program. So this will accurately produce 5 millisecond delay in my program. So this particular function now right over here is useful for generating accurate time delays using the timer 2 peripheral of the microcontroller. So this is the accurate millisecond delay function using timer 2. So if I want to produce delay of 1 second, I can write value 1000 to 1000 as the parameter for this function call. So this will generate 1 second delay and this will generate accurate 1 second delay, that is 1000 millisecond delay. I'm just compiling this program. The compilation is successful with 0 errors and 0 warnings. Now I have already connected my nuclear development board to my PC through USB cable. I'm just dumping the flash to the microcontroller. Now you can see this is the development board. I'm just resetting the board for running the program. You can see the LED is blinking at a rate of accurate 1 second using timer 2 peripheral of the microcontroller. So in the scope you can clearly see for every second the PA5 pin of the microcontroller is toggling. So the pulse generated is mostly accurate. So I hope in this video you learned how to configure the timer for generating accurate time delays in your program in the microcontroller of STM32F446RE. Similarly, you can use any timer of this particular microcontroller for the same purpose. The only change is the pointer that you are configuring will vary. See you in the next video. Thanks for watching.